Hello all, in this lesson we will be studying concentration part 2, meaning we're going to do just a couple extra versions of calculating concentration. That would be volume, percent by volume, and also parts per million. This one's pretty common. And I'll teach you how to prepare a solution of known concentration. Alright, what you need to copy down is the header, which is really, the homework is from yesterday's assignment, so just we'll continue that. And then the second thing you'll write down is today's aim, which is what is concentration, day 2. And these are our do now questions for today. So copy those down, but don't answer them, we'll do them in class. Alright, so we may have hit against a question that was particularly challenging in the homework yesterday. So it looked like this. It said if 100 milliliters of a 1 molar solution is evaporated to a volume of 25 milliliters, what will be the concentration of the resulting solution? So it's best to do this in two parts, and in the first step what we're going to do is figure out the number of moles of solute that are in the original solution. The reason why we're going to do that is because in the second step we're going to deal with the idea that some of the volume of the solution has evaporated, but that only the water would have evaporated, but not any of the solute. So we'll calculate a new concentration. But first step, we need to figure out how many moles were in the original solution. So let's start with that now. Write down your very first thing, which is your given information, and in this case it's going to be 100 milliliters. Because molarity is a concept that deals with liters, we need to convert this milliliters into liters. You may know that there are 1,000 milliliters in a liter, and we can construct our conversion like this. I chose to put milliliters on the bottom because it will ultimately have the effect of canceling the milliliters on the top from the previous scenario. Alright, so at this point what we have is, I'll go ahead and cross out the milliliters. But what we have right now is liters, and we need to eventually get our answer in moles. The next bridge that will help us get from liters to moles is to use molarity, which is moles per liter. Check this out. So I wrote in moles per liter, which is our way of saying molarity, which is the capital M. So this capital M and this moles per liter are the same thing. And I used the 1.0 because what this is really saying right here is it's saying there's 1 mole in a liter of solution, which is also what I said down here, but I was a little more clever about it. I designed it this way because I would be able to cancel the liter with this liter, and my answer would ultimately come out in moles, which is great. So that's what I was trying to do. So let's go ahead and calculate this through, and ultimately it's going to be 100 times 1 times 1, which is 100. But we do need to divide it by the 1,000 times 1, which would be 1,000. Some of these zeros are going to cancel. These two zeros and these two zeros will cancel, so we're really ending up with the calculation 1 over 10. So the final answer here is 0.10 moles. So now we know that there were 0.10 moles in the original solution. But, as the question stated, it was evaporated down to a volume of 25. Now when that evaporation happened, you did lose a great deal of water, but you didn't lose any of the solute, whatever it was. So all of this 0.10 moles that I just solved for that I must have had, it's still there. But the 0.10 moles is present in a new volume, which is 25. That's going to make it more concentrated, by the way. So when I do my final calculation for what would be the concentration of the resulting solution, I'm going to go back to my age-old equation for molarity. Molarity is moles per liter. The number of moles did not change. It was 0.10 and it still is. And the number of liters did change. Instead of being 100 milliliters, we now have 25 milliliters. In terms of liters, we need to divide that by 1,000. So I got 0.025 as the number of liters. Alright, so let me go ahead and take that 0.025 and put it down here. And I'll do 0.1 divided by 0.025. And I am getting 4 as my answer for that. With sig figs, I'll do an extra digit. And the unit is moles per liter, because both the moles and the liters remain. But some people would just write 4.0 molar, because those are the same thing. Alright, so here's a new one for you guys today. It's called percent by volume. I don't believe it's on your reference table, but it's also extremely easy to remember. Let me just rewrite it here, because it looks like it got a little messed up with the formatting. Alright, there it is. So it's going to be the volume of the solute over the volume of the solution times 100. Typically, this is volume over volume because it's liquids dissolved in liquids. Like, for instance, alcohol dissolved in water. You've probably seen 70% isopropyl alcohol in the store, 90%, 99% isopropyl alcohol are all available. But the percent is telling you the volume of the alcohol over the volume of the total solution times 100. So let me show you how to do this one. So it says, what's the percent by volume of alcohol if 50 milliliters of ethanol is diluted with water to form a total volume of 300? So total volume of 300 means that that's the volume of the solution. I know in previous questions we would add the 300 to the 50, but in this case this is already the total volume. So I'll set up my equation, and I'll multiply by 100%, and I'll get 16.7%. With sig figs, I think we look good with those 3, so that's my final answer. Now, parts per million is a little more tricky, and it's only used when you're dealing with an extremely tiny amount of solute dissolved in a relatively large amount of solvent. As an example, I suggest thinking about a swimming pool. Most of us know that swimming pools have chlorine dissolved in them. Chlorine is a toxic gas, and it's used because it will kill bacteria and other microorganisms that are in the water. However, the chlorine can also kill a large animal if it were present in large enough doses. So we're very careful to keep the chlorine at a very, very, very low dose that's toxic for the microorganisms but not to the larger animals. So here's how we solve for it. Parts per million is exactly what it sounds like. It's how many parts of a substance are in a million parts of the solution. So that's how you can tell it's very small. So you take the mass of the solute and you divide it by the mass of the solution, and you multiply it by 1,000,000, because this is going to be ultimately a very small number by itself. So we multiply by 1,000,000 to make it more reasonable. Here's a practical example. A swimming pool might contain about 2 grams of chlorine in 1,000,000 grams of swimming pool water. A fact that you'll need to carry with you is that 1,000,000 grams is going to be equal to 1,000,000 milliliters, and that's because a milliliter of water is equal to a gram in terms of mass. So if I represented this idea with molarity, it would turn out to be very, very small and very difficult to interpret. So we use parts per million instead. Here's a question I pulled from your book. Approximately 0.0043 grams of oxygen can be dissolved in 100 milliliters of water at 20 Celsius. Express this in parts per million. So there's my equation. The mass of the solute is going to be 0.0043 grams oxygen. And the mass of the solution would be all the mass of the water plus the mass of the oxygen. So I'm going to write in 100.0043. And this is me being sort of a goody two-shoes, because I know that this solution contains a tiny amount of oxygen, so I wanted to include it in the mass of the solution. But ultimately what I did was I took the 100 milliliters of water, I acknowledged that a milliliter of water has a mass of 1 gram, so I said that it was 100 grams, so that's where the 100 comes from, but I added in the mass of the oxygen, so 100.0043. I will point out that there are some multiple choice questions that are even in your book, and I've seen in previous exams, that do not do this sort of goody two-shoes thing, and they'll just say a 100 in the bottom. But strictly speaking, mass of solution would also include the very tiny mass of the very small amount of solute. So if you're doing a short answer, I strongly encourage you to be a goody two-shoes as well. But if you are in a multiple choice and the answer that you want, meaning like with the extra mass, isn't added and there's no choice, then just go with the regular answer of 100. Okay, so let me calculate this. So I'm getting 42.998, but with sig figs I only really need 2 of these digits. So I'm going to go with 43 parts per million. And whether you had been a goody two-shoes or not, you would have gotten that answer. So don't panic. All right, here's how you prepare a solution of known concentration. As a focus, here's a question. What mass of sodium carbonate is required to prepare 2 liters of a 0.25 molar sodium carbonate solution? So there are a few things to think about here. The first thing to think about is that we don't have 1 liter, we have 2. The second thing is that we have a 0.25 molar solution, which means that if we had a liter of the solution, you would only need 0.25 moles, but we have 2 liters of the solution, so we really need twice this number of moles to keep the same concentration. But additionally, we're going to need a gram formula mass, which is the link between the mass and the moles of the solution, because right now all we can really say is that we're going to need 0.5 moles, but we need to convert that into mass. So let me put some of this down on paper. So the 0.250 moles for 1 liter is a reference to this guy right here, the 0.25 molar. Let me highlight that for you. So I did a proportion, and I was just working it out because I know that in the equation or in the question it asked me to actually prepare 2 liters. So I wanted to show that down here. So there's my 2 liters, but I put 0.500 moles, which is twice the amount of the moles from there. So it's going to be the same ratio, but it's going to be a larger volume. So I know for a fact that I need 0.500 moles. But the question asks what is the mass that I need, so let me convert this number of moles into a mass. I'm going to need a gram formula mass. Check this out. Sodium carbonate is made from 2 ions, the sodium ion and the carbonate ion. And the carbonate ion has a -2 charge, so I'm going to need 2 sodium ions to neutralize 1 carbonate. Hence the formula Na2CO3. But I do need to figure out the gram formula mass for that guy, so check this out. Sodium has a mass of 23, carbon is 12, oxygen is 16. I'm going to put in their quantities now. So 23 times 2 is going to be 46, 12 times 1 is 12, and 16 times 3 is 48. Let me sum. I get 106 grams per mole. So I can put this in here to do my conversion. The 106 grams can go on top, and the 1 mole can go on the bottom. Mole will cancel mole. And I need to multiply 0.5 times 106. And I am getting 53 grams. So that, of course, is going to be my final answer for the mass of sodium carbonate needed to produce 2 liters of a 0.25 molar sodium carbonate solution. Now, from a practical standpoint, the Regents may ask you like the physical steps that you would need to do to make this solution. So after you've figured out the mass of the solution that you need, like we did here, then you should measure out the desired mass and add it to an empty flask that has some volume markings on it. Then you add liquid just to cover it, and you swirl it and let it dissolve as much as possible. And then finally you'll add more liquid until you reach your desired volume. And it's helpful to add the liquid in 2 steps because of splashing and spilling. So if you just put a little bit in first, then you can get it all stirred really vigorously without making any spills and any splashing. So it's a safety thing. Alright, so copy down these pair-up questions. We will solve them in class though, so don't do them until you see me. And these summary questions, please copy these down as well. Don't answer them, we'll do them in class. Thanks for watching, everyone. Have a great night.